Hello.
I wanted to say hello.
Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Kaise hain? Everybody is fine? Everybody is dead. Sad. Everybody is sad. Okay. Sad or sad or sad? What they are saying? So university is online? Everybody is depressed and they are probably dead too. Okay. But do we really need to be sad? So much of it. If I ask you a question fairly, it is really a major big deal. I mean, it is a matter on which you kill yourself, or start firing in the air and kill 3 people and injured another 30. Is it really a behavior of any nation to do this? I think we need to be sad on something different, not on losing a game. We need to be sad that we are at least 50 years behind our neighbor. We started from the same position. We need to be sad that they have a stable democratic institution, they have a good judiciary, they have excellent science structure, they have universities, they have opportunities for young people to grow, and they have 32 satellites in space. So ये चीज़ें हैं जिसमें हमें compete करना है. So what I did actually yesterday, and I'm telling you with absolute honesty that I really worked extremely hard, and I made sure that a bit of me can do something better for this nation. I think this is what we need to do. आप सोचें कि as a nation we missed an extremely important opportunity of making people realize that we need to compete in other grounds also. There are other things. बहुत कम ऐसा होता है that a nation is focused on something. This was an occasion in which the whole nation was focused, especially the young people. और इस वक्त अगर हम बात कर रहे होते, अगर मीडिया हमारा बात कर रहा होता कि make sure that if you want to compete in the world, start working 7-8 hours every day after school, start learning science and technology, compete in every ground on the face of the earth for development. कितनी अच्छी opportunity थी जो हमने miss out किए. Nobody even talked about it. We just talked about a lousy game. It can be a game, and there are lots of games also. We have a better record than India. We have beaten them more time than they have done to us. But would it really make a difference? It doesn't really make a difference. I want you to read a very thought-provoking book called Blood and Snow on Kargil crisis. It is available on internet also, written by General Verma, and this would tell you how nations commit blunders. Thoughtless, brainless people can really affect the life of the whole nation. That is a tragedy. We need to be sad that we actually lost half of our country in 1971. So that is this make me sad that you think that you cannot do anything. You can do lots of things. Every individual is responsible of a nation. You see, we collectively make a nation. Nation कुछ नहीं होती. There is nothing like anything. कोई animal नहीं है जिसका नाम nation हो. Each one of us is an integral part and a component, and we are so blessed that everybody look towards us to get inspiration. कितने बच्चे हैं, कितने cousins होंगे आपके, कितने बहन भाइयों के बच्चे होंगे जो आपकी तरफ देखते हैं inspiration के लिए. So you are a role model. I think you need to change, and if we change, then the whole nation change. Nation is nothing but a group of people who have same inspiration, who have a spirit, who want to do together something, and they have the same future become nation. A group of people who are disintegrated, who have no hope and aspiration, who have no common goal, they become a mob of people together. We were integrated for a few days, and I really feel very sad that we didn't really use this opportunity of making people realize, honestly. We were so focused on one point, and that point was winning of Pakistan. And we could have added in that we can win as a country on some other things too. Believe me, we missed a very important opportunity. These opportunities doesn't really come handy. They come after years of it. The whole nation was focused on one point, that we want to win. And this strong desire to win can be converted into a very positive force. Believe me. I feel extremely sad that none of us have actually used this, neither the media nor the politicians. So,
because on the channels, the people who are talking all belongs from the same field, so they talk
nobody,
similar.
bilkul.
I mean, educationist has to be there to talk about this way. It's a visionary talk. So
That is what we need to do. We need to have a vision for this nation. So remember, each one of us can make a whole lot of a difference. Individuals can make a difference also. And each one of us are responsible for our act. जब हम कब्र में जाएंगे ना, तो Allah would actually the act of others, but what we have done in the face of the earth as a responsible citizen of a nation which was created with the sacrifice of 5 million people, This is an amazing nation which was created with the sacrifice of 5 million people. No one in the history of can claim. We have Yasin sitting there, he's from Palestine. His third generation is fighting for the independence. Third generation is fighting. And see, we got an independence, and then we lost half of the country. And then we are verge of losing everything else also, God forbid. So we need to be alerted, and we need to do whatever possible in our sphere to do positive things around us actually. Okay, before I get extremely passionate, let's start NMR. What is this? Shall I just start later? Okay. But what I really want to know, Bismillah ar-Rahman, that what we have discussed day before yesterday has been absorbed at least partly. Because you see, I do not really expect you to understand NMR fully without an extensive reading yourself. No course in the world. I can challenge that you go to internet and you can look into videos of people who are explaining NMRs, and you can download MIT's or Cambridge lectures. You would not really find any course which can explain everything to you. Either they are extremely advanced or very fundamental. They can't take you from very fundamental concept to advanced concept in one go. NMR itself requires many courses if you want to understand the whole concept as a whole. But remember, kindly recall the very first discussion which we had when we first met, that I said it is important as a student of chemistry, as a student of biochemistry, that we are aware of the potential of NMR spectroscopy and the myriad of information it offers. We need to be aware of the fact that this very expensive piece of equipment is not only for recording proton NMR or C13, it can do lots of other things too. It can do structural elucidation, it can do lots of conformational analysis, you can study exchange spectroscopy, you can understand drug receptor interaction, you can do so many things from the same investment which we have made. I visit lots of laboratories in the world. People invite me to different laboratories all over the world, and it really hurts me when I see that these extremely expensive machines are actually used for very trivial experiments, maximum to the COSY or NOSY or whatever. The machines are capable of doing lots of other things too, And as we would hopefully, as we would move forward next week, I'll tell you what else it can do. I mean, there are so many other things which these NMR machine can do. So my objective was always to give you an introduction of a very powerful technique, to give you a basic set of understanding so you can build by yourself by reading yourself. This what I did also. You see, I have never learned NMR spectroscopy as a regular subject. Of course, I attended a few courses, but these courses were either extremely difficult, like Jackman's course, where there was all differential theories, or very fundamental, where people have actually spoken only 4 or 5 lectures about some NMR experiment. What I am trying to do is to take you through all the steps from basic learning to the advanced learning, with the hope that the fundamentals would be clear enough for you that you can sit with the book and then read 4 or 5 times, several books maybe, one after the other, and you would understand it. I guarantee that you would understand. Some of the terminologies look extremely scary, like multiple quantum or single quantum or double quantum, coherence transfer, polarization. But they're essentially very, very simple techniques. The terminologies are quantum mechanical terminologies, but in reality they are very simple. Now, I want to ask you, what we have discussed last time was that we briefly went through again with the TOXI. We studied in greater detail inverse NMR spectroscopy, and then I started to discuss about NOE. NOE I start afresh. I'll start right from the beginning. But anything before that, if you want to ask anything, I would be very happy to respond to you. Okay. So they're locked with a spin lock, eh? Okay. And that was in TOXI, I believe, eh? मुझे याद नहीं रखता. This this is a concept which you would be able to appreciate if you go quickly through the understanding of COSY. Remember, COSY was a 2-pulse sequence, 90X and 90Y. Right? In the COSY, we convert longitudinal relaxation into a transverse relaxation, and then we wait for the coupling partners to split and go to the antiphase, and then we carry out a 90Y pulse, and that 90Y pulse serves as a technique in which polarization of A is transferred to the polarization of X, and if we are focusing on X, the X polarization is transferred to A. That was the basic concept, and we learned that we remember this. I showed you and I told you that this is the best figure, a diagram which I was able to get is explaining COSY. I don't know where that. This one. I told you that this is the result of a 90X pulse, right? And this is evolution time. And during this evolution time, this is a homonuclear experiment. A and X. A is coupled to X. A is a doublet. X is also a doublet. So in reality, on the XY plane, after some time, you would have 4 vectors, right? 2 belong to A and 2 belong to X. And remember, when you bring them together, by a 90x pulse, this is called coherence. This is a coherent signal. There is no splitting took place yet, neither because of chemical shift nor because of coupling constant. This is a coherent signal. And I can tell you that you can keep this signal coherent by giving a 180 Y pulse after an interval. If you keep doing it, this would always be focused. This would always be coherent. Right? This is, we understand very clearly that 180 Y pulse right after a 90x pulse, so many of these 180 Y pulse will keep this magnetization coherent, and they would not evolve because of chemical shift difference. Okay, just forget it right now. For the time being, just forget it, and I want you to forget the 4 peaks. Just remember the 2 peaks of AX. A is splitted because of X, and X is also a proton. It's a homonuclear system, right? Now, this is a coherent A peak, and this coherent A peak will divide into 2 components because of its coupling with X, and these 2 components will move away from each other in this evolution time, right? So if evolution time is 0, there is no splitting, right? Evolution time less, like 1 or 2, then you would see some evolution, some modulation, some splitting of the signal. When evolution time would be larger, they would move away from each other, right? So when evolution time is small, they have split it, but they have split it very closely. They remain close to each other. Not enough time, right? They just split it like this, because the evolution in XY plane is a time dependent phenomena. More time, they would go away from each other, more time, right? So this, मैंने क्या किया था? Oh God. Sometimes I really think that everybody has a restart button. Sometimes it's better to restart all over again. Okay, so without wasting time, kindly remember that with the T1 time, very small T1 time, the splitting is very, very less, right? And these peaks are called in-phase peak. And with the larger T1, they would go away from each other and they would reach to a particular stage when they would be anti-phase to each other. Right? So there are 2 situations. One with the less of T1, when T1 is small, then you would have a situation which is in-phase situation. The second is a situation in which you have anti-phase of this doublet, right? When you give a 180 Y pulse or 90 Y pulse, sorry, in COSY, the in-phase situation, in-phase जो है, would not really change much. They would just go a 90 degree. They would remain in phase because they are not modulating. But when it is anti-phase to each other, the 90 Y pulse will take them to Z and negative Z. This is a situation in which A change information coherence with the X, and X change the coherence with the mixing of coherence takes place, and that mixing of coherence develop appear as a cross peaks. appear as a cross peak, right? So in a correlated spectroscopy, the diagonal peaks are generally the results of in-phase magnetization, and the cross peaks are the result of anti-phase. And I think it should be that clear to you, damn clear to you, that clear, sorry. It's not a polite word anyway. Do we understand COSY now? Really? Okay. So this was this beautiful, nice slide which I like very much. This one. Where is this one? This one. And this one is representing so-called in-phase component, when the components have not really moved apart from each other, far away, and this is the condition when they are anti-phase, right? Where they are anti-phase. And remember, I want to tell you something interesting. I want you to avoid it, but somehow I need to tell you that anti-phase cannot be detected. This is a zero peak, right? So this is the peak. If you want to make anything silent, if you want to disappear, if you want to make sure that it goes out of the system, then what you need to do, you have two ways of doing it. Either you saturate or you make it antiphase, right? You can make it antiphase. So anyway, this antiphase is a situation when another 90 vipers is provided. And when you make them 190 vipers, they then become mixed with the X spins, right? The X spin के साथ जो इसकी mixing of coherence is called coherence transfer. APT में is called polarization transfer, coherence transfer, polarization transfer, population transfer are exactly the identical terminologies. Exactly identical transfer. Coherence transfer from A to X and from X to A leads to off-diagonal peaks. Okay? Leads to off-diagonal peaks, the cross peaks, right? Because A is modulated. Modulation means affected. A is modulated by X and X is modulated by A. That's why you see a cross peaks, and these cross peaks are then used in COSY spectrum as for coupling partner. What I moved forward was that in the correlated spectroscopy, despite the fact that it is a very powerful technique in which you have cross peaks and diagonal peaks, and you can relate geminal, vicinal couplings, protons, you may face a problem of overlapping. I don't know whether I showed you earlier, but overlapping is a serious issue. For instance, in this case, you see the 4 and 5 are overlapped, and these 4 or 5 proton, they cannot be correlated because they are so close to each other that you don't see any of cross peaks between them. So this is a powerful technique in which you have dispersion of proton signals in two frequencies, where you can correlate things. Still is a problem by number of things. You cannot distinguish between geminal and vicinal coupling. You have to trace a spin system one after the other. You link A with the B, B with the C, C with the D, and then you trace the whole spin system. But you can face with a situation in which we have an overlapping of signal. Okay. So anyway, this is a good spectroscopic technique, and I said this is not only for proton, it can be for phosphorus also. Phosphorus is a fairly abundant, and this is the philosophy which I told you. And what then I moved forward was the TOCSY, total correlation spectroscopy, and I hope I would be able to explain it to you by using this. Now, the difference between COSY spectroscopy, the pulse sequence of COSY and the pulse sequence of TOCSY is that instead of a 90 Y pulse, instead of a 90 Y pulse, it is replaced by a spin lock pulse. Spin lock pulse. So instead of, remember, COSY has two pulses. TOCSY has two pulses also, but one is a composite pulse, and one is called train of pulses, or is called trim pulses together. And it is also called MLEV 16, 17, 18, 19, 20. And 16, 17, 18, 19, 20 means nothing but so many types of trim pulses. So this is Malev 16. If you count, you would be able to count 16. I'm not really sure it's 16 or whatever. But this spin lock is an interesting phenomena, and this is called mixing time. This is called mixing time, and mixing time is a constant time interval. You don't vary that, right? So when I said 20, 40, 60 and 100, they are different sets of experiment. Different sets of experiment. It doesn't really mean that you are changing it every transient. Every transient में आप change नहीं कर रहे. You know, whole collection of transient for 20 millisecond would have only one variable, and that is your evolution time. Evolution time is incremented. Evolution time is uniformly increased, but the mixing time kept constant. In one set of experiment, it is kept constant as a 20 millisecond, other 40, 60 and 100. But I'll tell you the consequences. But now, you see, by using a vector diagram, one can understand the whole thing in a much clearer way. This continuous pulse or spin lock pulse on Y. On Y. Kindly remember, this is Y. So this is the Y is the place where you actually brought your magnetization after 90x pulse. So if, for example, if I tell you that a 90x pulse is provided and T1 is 0, and then a spin lock is provided, you would very quickly be able to recognize that there was no time for this to split, and if there was any split because of any reason, magnetic inhomogeneity, experimental errors or little coupling or whatever, would be locked by a constant train of 180 Y pulses. 180 Y pulse in front of the magnetization would mean that it will just flip like this, right? Component here will go here, right? If it has divided into two parts, this move like this, become a mirror image constantly. And if it has not been splitted, then it has not evolved at all. There is a zero evolution. T1 times 0 means that there is zero evolution, and they remain forever on Y as a coherent signal without anything, without any splitting by 180 Y pulse. Remember, this is a condition which you have forced a system. Now, when they are not evolved, when they are not splitted, would they have a different chemical shift? They would never have a different chemical shift. Chemical shift means offset, differential frequency from a reference frequency. And they have not been offset. They have not evolved. They have not splitted, right? So since they have not splitted, they remain on the same chemical shifts. So we have a 1000 proton, T10, mixing time means no splitting at all because of chemical shift. Remember, now I want you to think that there is an incremented time delay. When there is an incremented time delay in which you let this coherent signal freely process on the xy plane, freely process, there is no force on it, it would divide. And the division of this peak, because of chemical shift, is dependent on the T1. Right? As you would have more T1, they would be able to move away from each other. But remember, at the end of a T1, as it was as 0, at the end of a T1 which is greater than 0, they have already split it. And when they have already split it, the 180 would do like this. Right? So it would never let them go away from each other. They would always be together because this is a train of pulses. As soon as they would try to diverge, you would give another spin-echo pulse right away and then they would remain. So whatever splitting has achieved during the T1 has been frozen during the mixing time. Whatever the T1 has been achieved. Remember, T1 is not a constant. So please see this experiment as an evolutionary experiment in which your coherent signal has been splitted based on the amount of evolution time. The evolution time you have given. So at the end of evolution time, as you finished this delay, you have a mixing time. This mixing time is composite of a fixed number of 180 spin-echo pulses. Remember, spin-echo pulses would never let chemical shift diverge. The spin-echo pulses will bring them together and will create a situation in which they are not moving away from each other because of chemical shift. Because you're constantly giving a 180 pulse. So as they split, you give a 180 pulse. As they split, you give a 180 pulse. Remember, the splitting is going on in between the mixing time also. This is a process which you can never stop. So during the first delta, they were split, very small delta. But you would give a 180 pulse, they would go like this. So the things which were moving away from each other would then move close to each other, right? Because this is spin-echo, and then they would move again forward from each other. So you would have one time delay delta in which they would move closer, and then the other delta they move away from each other, and then 180 bypass, and then. But remember, the T1 has already taken them to a different position. They are not at the same position in T1 0, T1 1 second, T1 2 second, T1 3 second. They are different from each other because the starting point is different, right? Do you kindly appreciate that T1 has actually evolved them to a different level depending on the T1 time. T1 time 0 means no splitting. T1 time 1 second means that they are splitted. And T1 2, 3, 4, 5, 6, 7, 8, 9, 10, transient, every transient means they are at a different position. So when you give a mixing time, they split. When you give 180 pulse, they come close, they again split, they come close, they again split, but they are all locked for chemical shift. You are not letting them to go away further. Whatever they have evolved during T1, that is fine. But during the mixing time, you are not letting them move away from each other. Tell me, T1 0 FID and T1 10 FID would be same or different? Absolutely. And they are different because the starting point is different. When the starting point is different, you would have a different FIDs. When you would have a different FIDs, you would have a different spectrum. And when you would have a different spectrum, the difference in spectrum is because of the T1. T1. Now I want to introduce another terminology. You can remember always that you can refocus chemical shift by spin-echo pulse. You can never refocus in a homonuclear system coupling constant. Never. Example, this is your two chemical shift. 180 pulse, this is slow moving, this is faster moving. When 180 pulse, this is like this. So this move here, they merge. But when you have a doublet, and they are moving away from each other, when you give a 180x pulse, they are also already relabeled. They continue to move away from each other as a free precession. As they are freely precessing. So at the end of the mixing time, you have two effects on it. One is because of chemical shift divergence depending on T1 time. And the other is this coupling constant divergence, which you cannot refocus by thousands of 180 pulses. They would continue to diverge from each other. Okay? Now, your FID is labeled. Your FID is now labeled by two facts. One, that chemical shift has not evolved. So even there are 6 or 7 or 8 different protons, they all are locked to each other. Right? But at the same time, despite the fact that they are locked to each other, their signal has split because of coupling. Right? So what you see in FID, pseudo FID, is this beautiful effect that every proton of a spin system has no chemical shift difference. Almost no. Kindly say almost no. They have just a small chemical shift difference. But they have evolved because of coupling. As a result, what you see is an amazing phenomena which is called spin locking, and there is a coherence transfer between all the protons of the same spin system, and it is a time dependent. Okay, spin mixing time, if mixing time is short, spin lock behaves exactly identical, but this chemical, because of the divergence, because of the coupling, is only visible for vicinal and geminal. When you give them a more time, you would be able to see that A proton is coupled with B, and then B is coupled with C, and then C is coupled with D, and D is coupled with F. So you see the coupling or network, whole coupling network based on mixing time. This is the beauty of TOCSY, and you see that these satellite peaks which appear in the larger mixing times are because of the coherence transfer took place during the mixing time. And remember the same philosophy, that diagonal peaks are representing when they are not modulated with each other. Off diagonal peaks are representing when you give them a time and mix them together. Okay? This is the philosophy, and I am sure you would be able to understand. Okay, in this case, this is a one-dimensional TOCSY. This one-dimensional TOCSY, you have this carbopeptide. You see, in this carbopeptide, there are 2 amide protons. Where's D? A, B, C, D. A, B, C, D, they are amide protons. 1, 2, God, where is 3? Okay, there are B and C. There are amide protons. These amide protons, these amide protons are then taken as an anchor. You take these amide protons. There are 3 different spin systems starting from the amide proton. These amide proton, this, and I think there is one more. I'm sorry. So there are B and C together. So there are 3 amide protons. Okay? Count it. B, C, D. D is this one, and there are B, C. So there are two units. So there are 3 different amide protons, and each amide proton has a different chemical shift. What you do, you lock every spin by giving in a specific pulse to the chemical shift of NH. And then everything which is coupled with the NH with reference to time is all come close to each other by a spin locking pulses. So what you see that this NH has coupling with all of these protons as you give the more time. And that's how you get a 3 separate NMR spectrum of 3 separate units, D, B, C. You should be able to have D also if you identify one. So that's how this is an extremely powerful technique. If you have a choice of giving a different mixing time, you would be able to see the emergence of other than Wassenel and geminal couplings with increasing mixing time. As the mixing time will increase, you would be able to see that these new peaks are appearing, which is because of NH, this, go further. Same analogy that with time, if you throw a stone in a static pool of water, the ripples go away from each other with time. And this magnetization, this strong magnetization which you give it to the central NH, say, in this case, you would see that this is spreading to other part of the spin system with time. This is the time-dependent coherence transfer. And if you read it through, I invite you to read second book of Professor Taur Rahman, the blue book, 1 and 2 dimension NMR spectroscopy. There is a beautiful description. It is lengthy, but I'm sure you would be able to understand the phenomenon. And I'll be happy to answer any question when you feel that you understand it. Okay? Understand it. I mean, no answer, no question. But I can, yes, I mean, you understand that. Yeah, your mixing time should never be more than relaxation time. Remember, if it is more than relaxation time, you get nothing. So it is therefore very important. Remember, we were discussing that we need to calculate T1 and we need to calculate big T2 also. Here you see a real operation of those phenomena, that your mixing time should never be more than T1. Because if it is more than T1, you would have nothing to mix. It will all be gone away, It will gone away. Whatever you try, your 180 pulses, remember spin echo pulses can combine them together but never stop relaxation. They would continue to relax back to the thermal equilibrium. Please kindly understand that in all of this phenomena, everything is done in a time frame which is much less than relaxation time. All NMR experiments are designed to make sure that detection starts before relaxation is completed. If relaxation is completed, you would have nothing on transfer plane. And when you would have nothing on transverse plane, you would not be able to detect it. So mixing time should be kept in a very precise way. Generally 100 millisecond is the maximum time you can go. More than 100 millisecond, you see disappearance of the peak, because the theta increase and they go back to the thermal equilibrium. Okay. Well, I want to come back to my this inverse was all right for you? Inverse uh, uh, inverse theta. You uh, are we sure that we understand the inverse NMR spectroscopy? That inverse NMR spectroscopy is a proton detected NMR spectroscopy. Kindly always remember that you cannot detect two nucleus at the same time. Please always remember. There is no NMR experiment has been designed so far in which you can detect proton and carbon together. One thing. Number two, please kindly remember that you can never record antiphase peaks, either on minus x or minus phi, or minus x or x, or minus phi or y. You cannot detect these peaks also. These are cancelling peaks which cancel each other also. Kindly always remember that you cannot detect anything which is not on plane, right? And kindly also remember that it is not necessarily be 100% on transfer plane. Anything close to transfer plane you would be able to see, because your detector has a big eye and it will be able to see something little up or something little down also. That is the reason why FID appears and decay. And when it goes out of the sight of the detector, you see nothing, right? So this is a situation. In inverse NMR spectroscopy, what you do, you in a traditional, you try to understand inverse NMR spectroscopy by understanding the polarization transfer, so-called real polarization transfer or coherence transfer or whatever, in which you transfer the polarization of proton to carbon. Remember, when you transfer the polarization of proton to the carbon, they are already on Z. But in order to detect the carbon, you need to give up 90Y pulse in order to bring the carbon to XY plane, because you cannot detect carbon unless you bring on XY plane. So they can be coupled in any position, but they can only be detected when they are on transverse plane. Always remember, if instead of carbon you bring proton on transverse plane and take carbon out of the transfer plane, then you would be able to detect proton, right? So polarization transfer is an experiment in which you transfer the polarization or population of proton to carbon by a selective population inversion, SPI, or a selective population transfer, ENAP जिसे कहते हैं. And by doing so, you label your carbon with the proton and you detect the carbon, right? So coherence transfer has already taken place, this time from proton to carbon. And if you do exactly opposite, I told you that coherence transfer, population transfer, polarization transfer are synonymous, they are same, they are not scary. When you think of coherence transfer, please kindly understand that coherent signal means coherent, and when you talk about coherence transfer means that this coherent signal is transferred to the other coherence. There's nothing, I mean, it's not a fancy word. Single quantum coherence means that alpha beta convert into beta alpha and you mix them together. Double quantum transfer means, double quantum coherence transfer means alpha convert into beta beta. So it's not a very fancy word, it is a very simple word. Now in inverse NMR spectroscopy, you take carbon, you do exactly the same thing, and you selectively irradiate one of the doublet peak of carbon. You do SPI on carbon peak, and as a result it is transferred to proton and you detect proton. During this process of transferring polarization, knowledge has been transferred. Modulation, coherence, mixing together means transfer of knowledge. always remember, if there are two protons which are not scalarly coupled, they don't share any energy level. And you cannot transfer any information from one to the other. Only the partners, CH or HH or CC, only the partner which are coupled scalarly with each other have the capacity of influencing each other during a coherence transfer experiment. जो coherence transfer, polarization transfer experiment है, this is the key to understand NMR spectroscopy. 90% of the NMR spectroscopy is just transferring coherence from one nuclei to the other. And in the process, you transfer the information. You have seen that when you transfer polarization from A to X, A is labeled by X and X is labeled by A. So that's why you see these peaks move out of the diagonal. Move out of a diagonal because now they are average of both. And you see that they are modulated. So during the coherence transfer, it's not only the population which is transferred, it is the information which is transferred. Now, if the inverse, in the case of inverse, you do with the carbon, right? You don't detect carbon, you just bring the proton magnetization to XY plane and you detect the proton, you detect proton NMR spectrum. But this proton NMR spectrum is modulated by coupled carbon-13. I'm so happy because I see some brightness in faces. And it doesn't seem to be because of Fair and Lovely, it is a real brightness. Yeah. Okay. Okay, now this scary name, heteronuclear multiple quantum coherence, somebody really tell me, that isn't it very scary? It just scare a person to the limit. Heteronuclear, proton carbon, right? Multiple quantum, of course there is a transfer of population from proton to carbon and carbon to proton. You are doing it twice. You're first transferring from proton to carbon and carbon to proton. So this is a two-time polarization transfer, and anything which is more than one time is a multiple time. Remember? So double quantum is also a multiple times. Multiple quantum correlation. When you correlate them, proton and carbon, and you correlated them by a very interesting experiment in which you mix the polar coherence of carbon with the proton and you detected proton, and this is a beautiful experiment. This is what we have learned, and this was very interesting also. I told you that the modern, this is the polarization transfer, a traditional polarization transfer in inept. Remember, inept, you have a proton, right? You bring proton, you evolve it, you achieve antiphase, CH, right? Antiphase. Kindly remember that CX is not in the picture yet. X is remain on the Z. You are just playing with the proton. When you just playing with the proton, after the end of this T1, when the doublet has reached to antiphase, you give a polarization transfer pulse or coherence transfer pulse also. The NMR literature is full of synonymous terminologies. Some people say polarization transfer, some people are so naive that they say population transfer, some people are so extremely advanced they want to use always coherence transfer, but just forget it. This is just a transfer of coherence, polarization, population by a selective population inversion, a 90Y pulse, which take H doublet into Z plane, right? When the H goes into Z plane, it adds with the carbon. And this is a polarization transfer. And during this polarization transfer, the coherence transfer, during this coherence transfer, because coherent carbon signal is mixing with the coherent proton signal. And when it is mixing with the signal, you see the labeling of information taking place, and then you bring your X magnetization, the carbon magnetization to XY plane, not to the proton. Proton remain there. When you bring it together to the XY plane, then you record a carbon-13 NMR spectrum, which is labeled by the information of proton, and it is sensitive because there is a greater population difference because of the gyromagnetic ratio. In this particular traditional inverse NMR spectroscopy, you do exactly the same thing with the X. H is not in the picture, right? H is remain on Z, right? Remember, you have the capacity of bringing H, X, fluorine, phosphorus, any of it, by using a fixed radio frequency, right? So here you are playing with the radio frequency of carbon. You brought carbon onto a 90 Y place, and then you let it split. The carbon would split because of proton, and at the end of the T1 time, it will go to antiphase. And when this doublet is antiphase, the 90 Y pulse will mix it with the H, which already exists in Z. And when you do that, then your population of carbon, which is a negative population, gyromagnetic ratio is so low, would mix with the proton, and then you bring proton on the XY plane, you detect it. And when you detect it, you see a proton detected spectrum. This is a proton spectrum because you have detected the proton modulation. But remember, during T1 time and during this selective population inversion, the proton is labeled by the carbon information. The information during the coherence transfer has been moved from the knowledge is modulated, proton is modulated by the carbon. This is the modern NMR, a modern inverse, which is multiple quantum coherence. You transfer proton polarization to the carbon, and then let carbon split, and then the antiphase carbon doublet is again given a pulse, and then it goes back to the proton, and then you detect the proton. So the source is proton, and you're detecting the proton also. It's much more sensitive. Philosophy is same, called multiple quantum coherence, because there are coherence transferred twice, right? Proton to carbon and carbon to proton. And we come to the end of the end of nuclear Overhauser effect. Okay. And if you feel that nuclear Overhauser effect is a difficult phenomena, you can give you comfort that only very few people in the world understand NOE, and you are among them, right? Okay, nuclear Overhauser effect. What you have done so far, by using all different technologies, different pulses, sensitivity enhancement, APT, etc., everything, what you have done, that you have assembled a structure together. You have structure in which you know this carbon is linked with this carbon linked with oxygen is linked with nitrogen, oxygen, carbon, nitrogen. You have a connectivity structure where you don't have structure of three-dimensional structure. Here you have NOE, and I told you that NOE was initially introduced as a factor in which the carbon intensity was increased at least threefold when there was a broadband decoupling. When there was a broadband decoupling, C13 NMR spectrum was recorded. People have seen an extremely interesting phenomena that the singlets were not the resulting collapse of doublet or triplet or quartet, but in fact the singlets were sometimes threefold more than they're supposed to be. And this threefold or less increase was then understood later because of the nuclear over-Hauser effect. But what is the real information which we get from NOE now is the three-dimensional molecular geometry. This is the main use of NOE. And kindly remember that it depends on internuclear separation. So when I say internuclear, it means 2 protons, 1 proton, 1 carbon, or 2 carbon. 2 nuclei close to each other in space, and they are not scalarly coupled. They are not bonded with each other by a covalent bond or anything like this. Or they are not hydrogen bonded. Remember, hydrogen bonding is a bonding. Kindly remember hydrogen bonding, how weak it is. It is a bonding. And you can see the effect of this bonding in the chemical shift. You know, when you record a hydroxyl group, it comes generally in the range of 4 to 5. But when it is hydrogen bonded, it comes about 8, 9, 10, 12, you know. So hydrogen bonding is hydrogen bonding. These are the two nuclei between two nuclei of a molecule which are close in space. And NOE depends on the closeness internuclear distances. Okay. In principle, you should be able to see more NOE when they are closer to each other. You would be able to see less when they are little away from each other. 6 angstrom is the maximum distance in which the NOE is observable. It may be more than, maybe 6 or 7 or 8 or whatever, you still have NOE, but you cannot observe it, you know. It's so weak that you cannot observe it. 6 angstrom is the maximum distance between 2 nuclei under which a phenomena of NOE is operational. There are 2 different types of NOE. One is called steady state NOE, very simple. Steady state thermodynamic NOE means that you give one pulse and you record. So it is a one-dimensional. So for instance, if in your molecule you have 2 proton HA and HX, you irradiate HA and you see the effect on HX. This is steady state. You know, you do a step and then you record it, one-dimensional NOE. The other is called transient NOE, in which you record the rate of building up of NOE. This is an amazingly interesting phenomena. You see, NOE is built with time. NOE का मतलब यह है the increase in the intensity of I. Remember I told you that S is the nucleus which is irradiated, source nucleus. I is a nucleus which is close in space to S, and it is receiving the NOE from S, and the increase in the intensity of I, the rate of increase in the intensity of I is a kinetic process, a process which slowly built up. So rate of building up of NOE cannot be measured by one-dimensional NOE, because in one-dimensional NOE you give saturation and you record effect on I. What is the most appropriate experiment to see what changes is taking place in I? How the NOE is built over I? Naturally two-dimensional NMR experiment. Because when you introduce a T1 in NOE experiment, you introduce an element in which NOE is building up. 1%, 2%, 3%, 9%, 10%, right? So this rate of building of NOE, the rate of building up of NOE is directly proportional to the internuclear distance. Now, you can tell me, you can ask me that you were saying exactly the opposite yesterday. And you can ask me that you said that you cannot measure the internuclear distances from the percentage of NOE, right? I was right yesterday also, and I am right today too. When you have a steady state NOE, the steady state NOE means saturation, giving some time, and then recording. Okay? During this time, relaxation is taking place because it's relaxation which is recorded. Remember what is recorded? It's just relaxation of I, right? So the rate of the NOE can build like this and can go up down. So it can reach to a 45, right? And then suddenly another relaxation pathway start functioning, and then you see a sudden drop of NOE. So in the steady state NOE, when you have a saturation and recording, you don't know what happened in between. You don't know absolutely. A lot of chemical reaction in which you see lots of things happen only when you do a kinetic studies. When you do a kinetic studies, when you follow the intermediates, when you follow the transition states. But if you just add reagents together and isolate a product, you just know that a conversion takes place. You don't know what were the intermediates, what has actually happened in between. So many things happen. Exactly the same phenomena that when you have a steady state NOE, one snapshot, give a saturation to S, record I after some time delay, there is no record of the provision of the building of NOE. Right? So in one-dimensional NOE, the percentage of NOE which you record at the end of the day means nothing. Okay? It is only through a transient NOE, NOESY, you would know precisely that the NOE is slowly building up or suddenly dropping out. Because you are recording this built up in T1 time. Over there, the delay is fixed. In two-dimensional NOE, the delay is variable, incremented. As a result, every time you record an FID, you know that NOE has built up. NOE is further built up. NOE is further built up. Or you would record that NOE is now start dropping. Right? So a snapshot would never give you a picture. The transient NOE, the rate of building up of NOE is directly proportional to the internuclear distance. If you can measure the rate of building up of NOE, rate constant of the building of NOE, that is directly proportional to internuclear distance. The percentage of NOE which you get in steady state and NOE experiment is nothing. It just tells you that they are close by. But if there is no NOE, it doesn't really mean that they are not close by to each other. And now we would go into this fascinating world that why it actually happened, These are the examples I told you that you can solve so many of these problems. And these are typical, very small, trivial problems in which NOE has been used. Much more complex than they are protein structures, DNAs, biopolymers, in which you have huge molecules folding with each other, acquiring a particular conformation, acquiring a particular tertiary or quaternary structure, and a proton which is 20 carbon away is coming close to because it has folded in such a way that you have a ribbon type or you have a flask type of molecule or something like this. For example, if I tell you that in the active site of an enzyme, there is a gorge. There is a place in which substrate is bound. And if you see that there is an NOE between this amino acid proton and this amino acid proton, you would know that this is the opening of the gorge. This is opening of the gorge. So you get lots of information. If this is one helix and this is the other helix, and you see them folding with the carbon hydrogen bonding, and you know that non-covalent interaction binds all DNAs. DNA are so strongly bound with each other because of the thousands of non-covalent interaction, proton-proton interactions, deuterining interaction, hydrophobic interaction, whole range of different interactions. When they are come close to each other, this is a type where you would be able to see the effect of irradiation of one proton on the other, if there's close to, or effect of irradiation of a proton on a carbon. Can be heteronuclear NOE, but you don't worry about that. And I want to tell you that the whole thing is very, very easy. This whole phenomena is just two pulses. One is a selective long pulse on S. Now remember, I am talking about a 2 nuclei NOE. Nuclei can be 3, 4, 5, 6, 7 because everything is close to the other, you know. When you irradiate one, it can affect several which are close to each other. But just for simplicity, this is S, which is pre-saturated. It means that you need to record a proton NMR and you must know the chemical shift of S. You generally like to, you see, when you are determining the structure, you have certain presumptions. You presume that this proton is close to this proton and you want to disprove or prove this thing. Okay? So this is your initial thought, thinking that these two protons seems to be close to each other in space. Because you see a certain weird structure or something like this. So you select one. The other phenomena is that you always select S, which is little away from the crowding. Because if you want to selectively pre-saturate S, it can't be in a multiplet. It cannot be with so many other protons, because if it is so many other protons, everything else will be saturated too. So it need to be little away from the crowding. This is the reason why if you have a crowding, then you go for a NMR in pyridine for doing steady state NOE. There are lots of other things which people do actually, but just two pulses. One big selective saturation, pre-saturation. Now selective means that this is not a pulse. It is just a saturation of S. Kindly remember, pulse means together at the same time. Pre-saturation, saturation, constant of resonance, decoupling or whatever, primarily means that you carefully selected the chemical shift of S, fix your radio frequency on that, and you turn on radio frequency oscillator for some time. Okay? So you have done this. Okay. What second thing is done is indiscriminate 90x pulse, which primarily means that everything which is on Z is now on Y. All the protons. It's not that you can select only I. You are not selecting only I. This is an indiscriminate broad width 90x pulse which bring everything on Y. Okay. Before that, you already have an NMR experiment. Aapko kindly remember that you have already recorded a proton NMR. That's why you know the chemical shift of S. So you have a very neat, nice proton NMR spectrum. Okay. When you do this experiment, theoretically, if S is close to I, the intensity of I will increase. Intensity of I will increase. So you would get a proton NMR spectrum in which S is pre-saturated, it is on the negative side, and anything close to S, which we assume is I, has an increased signal. Let's say about 5%. If you want to differentiate between, if you want to measure, what you would do? आप क्या करेंगे? If you want to measure the 5% increase in the intensity of I, what you would do? You will do what every intelligent person would do. Means that you would not do anything, right? No, actually it means that you would minus your proton NMR with this proton NMR. When you minus this proton NMR, or the original proton NMR with this proton NMR, you will see what? Only I signal. And the percentage increase. Finish, end. That is called NOE difference spectroscopy. NOE difference spectroscopy, what you have done, you recorded an NOE, proton NMR, NOE, and I'll tell you how NOE is developed, but just at this stage, it is important for us to appreciate that the intensity of I has increased. 5%, 10%, 20%, and it is among so many protons. And it is difficult to measure the intensity increase on I or anything else which is close to S, because it's not necessary that S give NOE to I. Anything which is close to S would receive an NOE too. But we are assuming that it is just a two-spin system. Okay. So the increase in the intensity of I signal in the full proton NMR cannot be easily detected. What you need to do is to just minus, your computer would minus the first proton NMR, जिसमें आपने इस तरह की कोई हरकत नहीं की थी, right? In which you had no NOE done. The simple proton NMR with this NOE proton NMR, and what you would get only those signals which increase in intensity. You will get only those signals which are increased in intensity, and you can calculate the percentage also. It's very easy, I minus I naught. But this is the figure on which I want to spend rest of my time. Okay. Kindly remember that there are two systems. There are two protons. Two protons. But it can be two phosphorus. It can be two carbon close in space. It can be proton and carbon close in space. Always remember that there is a generalization phenomena in NMR spectroscopy. What you have learned so far is equally applicable on nitrogen, on other things, So just remember that this is a generalized phenomena. But let's assume that you have two protons. One is S and other is I. Since they are close enough in space that they are interacting with each other. If they are not close in space, they would never share energy levels, right? So they are close enough, but they are not scalarly coupled. So you won't be able to see any splitting in their signals, right? What you would see is just that they are sharing their population by dipolar coupling. So you have alpha alpha, alpha beta, beta alpha and beta beta, and I don't need to tell you that this is the transition of phase, and the double arrow is showing that it can go up and it can come down. This W means possibility of transition or relaxation, both. S means on S spin, right? 1 means that during this particular possibility of excitation and relaxation, the nuclear spin of only one nuclei is changed. So the magnetic quantum number is 1, means that only one of it, alpha alpha to alpha beta, this only S is converting into beta, right? इसमें कोई शक तो नहीं है? So this is a transition which is called single quantum transition. Single quantum is just nothing but an orientation of spin. Okay, this is a single quantum transition. This is a single quantum transition, this is a single quantum relaxation. Single quantum transition, single quantum relaxation. From here to here, the spin of I has changed. Probability is 1. Magnetic quantum number is 1. Only one spin has changed, right? It is also a single quantum excitation and single quantum relaxation. From here to here, there is a change in the transition of S in the orientation of S, and this is also a single quantum transition. And this is an excitation and relaxation of I spin, and this is also a single quantum relaxation. Kindly recall, always remember that in a quantum mechanical understanding of NMR spectroscopy, it is only the single quantum which takes place. All the excitation and all the relaxations are always single quantum. Okay. So though we would have a 4 energy level, but relaxation from here to here would always be through this step or this step, right? So beta beta would never directly convert into alpha alpha. Reason? Very simple. That you don't really have a sink which can absorb so much of energy, right? Number 2, that why it will do it, it can do it in a stepwise manner, why it will go. Similarly, the excitation is also very difficult because you don't have a radio frequency strong enough which can excite everything to that level also. Now, this single quantum. What you have done, अब आप देखिए आप, I want to now give you another glimpses. If somehow, because of any reason, beta beta can convert into alpha alpha, this would be a double quantum transition and double quantum relaxation. Or this alpha beta can be converted into beta alpha. This is also a double change, isn't it? It is a double change. It is also a double quantum, but it's a zero quantum because you don't see end of the day, it's just alpha beta, beta alpha, right? And they are homonuclear systems, so you don't need to worry about that. Energy level is almost same. Now, this is the situation which I want you to concentrate. Remember that when you have energy levels, when you have energy level, you have population in those energy levels. That's how you record proton NMR. You know, there is a population difference which eventually emerge as your peak. Right? That is what you... So in this case, population is n plus delta. Delta is just a factor, an effect. N plus delta. This is the lowest energy state, right? And this is the highest energy state. And this is n minus delta, so it has a slightly less population as compared to Boltzmann distribution axis. Always remember, Boltzmann distribution axis. In these two intermediate energy level, the population is n. Okay? So now, if you want to see how S will appear in your proton NMR spectrum, S will appear difference of this and this and difference of this and this. Right? So what is the difference of this and this? Delta. अब आप लोग ना बड़ा फोर्सफुली सर को यूं हिलाएं वरना मुझे कुछ पता नहीं चल रहा. Honestly, चाहे आपकी गर्दन को कुछ हो जाए, I don't care, but I want everybody to shake his or her head either like this or like this, because I really want to have a feedback. Okay. The signal of S is the population difference between these two energy levels, right? And the population difference n plus delta, and n is only delta, right? And this is also delta, right? The difference is delta. In I, the difference is delta, and this is delta also. The difference is only delta. Now, if I want to tell you that this is a real proton NMR spectrum which you recorded the first time. Okay? Now you know the chemical shift of S. And now you bring a radio frequency oscillator, give a pre-saturation right on the chemical shift of S. So when you give the saturation to S, what will happen to S? S will disappear, believe me, because S is not present anywhere. But this is happen that the energy level they are sharing with each other, there is a transfer of the population of S which has taken place from this to this and this to this. So this was a delta. This is half delta. It means half delta has gone to here. So population kahan se kahan transfer hi? Population has transferred from here to here, right? And from here to this has decreased half delta, and this has increased as half delta. Now, if you look into the S, the population difference between them is now 0. So you don't see any peak, right? But the population difference between I remain 1, right? Remain 1. As a result, you would be able to see I. Right at this point of time, when you force your system with two different actions, one pre-saturation on S for a longer period of time, and the second is indiscriminate 90x pulse to bring everything on XY plane, including I, you have a situation in which single quantum relaxation is not sufficient to achieve a thermal equilibrium. Thermal equilibrium cannot be achieved by single quantum relaxation because system is uncomfortable, it has lots of energy need to be taken out of the system, and eventually a thermal equilibrium has to be achieved. The single quantum relaxation single quantum relaxation, it's not sufficient to do that. What will happen is the most fascinating thing which people have discovered, Albert Overhauser in some other case, is the following, that when a situation like this happens, when you have a strong energy into the system and the system is trying to achieve a thermal equilibrium, another relaxation mechanism will triggering कहलाता है. This trigger, and this mechanism is a double quantum relaxation. The NOE is double quantum relaxation. NOE is because of the double quantum relaxation. Because the single quantum relaxation would not increase any population. It is because of the double quantum, and you would see it now, right now. When there is a double quantum relaxation, it means that from beta beta to alpha alpha, some population will be transferred. Okay? Some population will be transferred. So this population transfer will do something extremely fascinating. When you bring population from here to here, जब आप लेके आते हैं, so you see the difference between I intensity increase, because this is a difference between them. ये कम हो गया. जब ये कम हो गया, so the difference, it has reduced. So this minus this would means more than delta, and this minus this would means more than delta, and that is recorded as a positive NOE. What you do, you just minus this spectrum from this spectrum, and you would get only the increase in the intensity in difference spectrum. Difference spectrum is nothing but original NMR spectrum is subtracted from the NOE. Now, another situation. In order to achieve thermal equilibrium, which primarily means achieving a population like this, another mechanism can trigger it, and that mechanism is a zero quantum. It is also a double quantum, remember, but net is a zero. So therefore some population is transferred from here to here, from here to here. As a result, the difference between them has gone down, decreased. Both cases. When it is gone down, you would see a negative NOE. So when you record a difference spectrum from this to this, you would see a negative signal, right? Because if it was 10, and if it is minus 2, you would see minus 2 peaks. Is basically a negative NOE. Negative NOE result because the population, because of this double quantum transfer, the population between two eye level has been affected. Now, question is that this population is affected by what? By pre-saturating the S. And S can only affect I when it is less than 6 angstrom close to each other. Otherwise, you would never have a situation like this. Now, I really want you to think in a very different way now. In a situation like this, there are many ways through which relaxation can take place. Number 1, W2 or W0, right? This can also compete with each other for relaxation, right? And W1 can also compete to some level. W1, although W1 would never be able to achieve a thermal equilibrium, but it can affect I population. I population may, this can still be operational. So there are competitive relaxation mechanism. Single quantum, zero quantum, double quantum. There are a number of mechanisms through which a thermal equilibrium can be achieved. right? If it is 100% W2, you get a nice big peak, positive NE. If it is 100% W0, you get a nice negative NE, which means the same. Which means the same. It means the same, that they are close to each other. They're close to each other. That's why they're influencing. If there is a competition between W2 and W0, they cancel each other. Right? One is creating a positive NOE, the other is creating a negative NOE. And if they are absolutely competitive, you get no NOE. Although 2S and I are close to each other. This is the reason why you cannot really rely on steady state NOE. That at the end of the day, the W2 can compete with W0, and positive NOE, the building of positive NOE is equal to the building of negative NOE. You would have nothing. You would have no, right? This is an extremely interesting phenomena. On top of it, you also have W1 operational in I. So W1 also compete. And how it compete? Longitudinal relaxation is an interesting phenomena. Longitudinal relaxation requires lattice, requires molecules around it. If you have oxygen, if you have particles of dust, if you have anything which can absorb energy, the NOE would never be detectable, because W2 would never come in place. W2 is only, this forbidden relaxation, only triggered when the system is forcefully taken to energy level and there is no other mechanism of relaxation. When there is a paramagnetic oxygen or a metal ions or some impurities, you would never get an NOE. This is the reason that you always, number one, NOE is a very tricky technique. Please try to understand that quantitatively it is a nightmare unless you go for nosy and rosy or whatever. Number two, that your sample need to be absolutely soluble, either in very non-viscous solvent or in very viscous solvent, like most of the proteins are viscous, right? Now, number three, that you must not really have anything which can trigger longitudinal relaxation. Your sample should be absolutely free of oxygen or air, right? It should be appropriately filtered. It should be 100% dissolution. It has a 100% dissolution. How you do that? You do a gasification, so-called degasification of your sample. Degasification of a sample is a very interesting phenomena. There are so many techniques for doing that. The one which I like most is that you constantly some inert gas like xenon or argon, which never trap inside, which has no polarity, that it remain in the, and this gas replace oxygen, pump out the oxygen. Number two is so-called freezing and thawing. You freeze it. During the freezing, you bring them together, and you thaw them. When you give them the temperature, the oxygen evaporates, it goes out of a system also. So there are plenty of different techniques. The one which we use in our institute is overnight degasification. We keep the tube and then we constantly introduce argon for a long period of time. It eventually evaporates. You have a sample free of oxygen, paramagnetic oxygen. Oxygen because it accepts energy very rapidly in order to convert. Okay, so degasification is important, and NOE is a very important technique for which you need to be extremely careful. For instance, this is a proton NMR, right? Regular proton NMR molecule. not the whole molecule, but just a component of this particular part. You irradiate methyl, a methyl, okay? It's so difficult to irradiate them together. If they're so close by, it is so difficult that you can irradiate them selectively. And this is one typical example in which both A and B gone down because the chemical shift difference is so little. You give a radio frequency pulse and then it really pre-saturates the system. So when it pre-saturates the system, the proton 3, whereas proton 3 is close, right, in space, although they're not scalarly bound, but anyway, you see this, and you see an intensity increase in H, different spectrum, because everything else is exactly identical in this spectrum, and therefore everything else is minus with each other intensity in H3. So H intensity different. You understand? You take this NMR spectrum, you subtract it with the fully NOE developed spectrum, and you would see only the increase in the intensity, and you can calculate the intensity also. Now, I give you some examples, and there are lots of examples of our own work in which we have actually solved lots of very, very interesting and complex problems. The literature is full. You can write a book on the use of NOE in natural chemistry. We have done lots of work on NOE. Anyway, you see that when the proton on this methylene are irradiated, there are 10% of NOE on H. 10% NOE on H, the same percentage which you have here. Okay? You can calculate the NOE, very, very simple. Number two, in another experiment, with H, reciprocal irradiation. When you irradiated H, you see only 6% enhancement in can somebody tell me the reason why it is actually happening? Same here also. Now, these are two E and Z isomers. This is a Z isomer, this is an E isomer. And in the E isomer, irradiate this, you don't get effect on olefinic proton, but you're getting effect on methylene. Therefore, you decide that it is an E isomer. Example of solving the problem. See, although other ways of doing that is just this one, that when irradiation of this methylene increase the intensity, it is Z, and where the irradiation saturation of this methylene, intensity of this methylene, they are E because they are close to each other. In this case, they are not close. Right? Now, let me ask you a question. Why always reciprocal NOE from this side is less than this side? You see, every time you're radiating this, NOE on this part, both in E case and Z case. Why, when you irradiate them, you get a less of percentage of NOE? Distance तो same होगा ना, चाहे इसको radiate करें, इसको radiate करें, they're the same distance. You're not changing the distance, right? Huh? Excuse me? You're getting close to it. I think everybody is attempting to understand. Absolutely. Hydroxyl वगैरह तो नहीं है, but ये मुझे कहने दें कि you see what is actually happening that when you irradiate H or this CH2, when you irradiate them, they have other partners too. On the other hand, this has no partner. It's far away. Or less partners or few partners, right? So the rate, the NOE effect of this proton on corresponding dipolarly coupled proton as compared to reciprocal NOE because of a simple NOE, simple fact that these part H or CH2s have number of other partners to which they can give energy. So remember, it is all relaxation. It is the I want to use a very beautiful sentence. Interplay of various relaxation mechanisms which eventually determine the extent of NOE. You can have an absolutely absent NOE because the W2 or W0 has never been operational. Now you can have a strong, nice NOE because there are no other mechanism operational except for W0, right? And you can have a weaker NOE, have so many of relaxation pathways competing with each other also. And you can have a system more than 2-spin system. It is not a 2-spin. There are in fact 3, 4, 5 different spin. So for this methylene, this is the only thing which is closed in space and with which it can play. But for this methyl and CH2, they have other CH2s also to which they can give their energy in and relax. Clear to everyone from other universities, because we might not see each other after NOE. We calculate. See, this is the way we calculate. The percentage. This is the H3I. This is I naught. I divided by I into 100 is percentage. You can calculate percentage of enhanced signals, in comparison to this. In comparison to you, just assume this as is a just simple differential experiment. So the percentage is calculated, but please remember that percentage is really not telling you anything about the distance between, but you have a 10% and 6%. Sometimes it's really much larger, 30% or 2%, right? So the reciprocal NOE, people don't attempt to go for reciprocal NOE because of a simple fact that reciprocal NOE doesn't really give you any added value to your experiment. It means nothing actually. Maybe perhaps some confirmatory, but can confuse you also, because it is possible that irradiation of this can give you 10% and irradiation of this give you 0%, because for this the environment is different and you have a competing proton which can absorb energy from the system, right? So when you irradiate this, you are creating NOE, not only this on this, but also anything which is close to it also. So remember, NOE is a very, very interesting technique, very tricky. You generally rely on NOESY. because it gives you a transient NOE. Some more examples of NOE. For example, you see in this particular conformation, these are two structures. In one, you have this side chain on N1, and in the other you have N3, right? Spin system would not tell you anything, would not really give you, but here you would see an interesting thing. This H is this one, this is fine. But this case would give you NOE which is there also. What would be missing? Because when you will irradiate 5, you would see NOE only on this, not on this, in this particular structure. This is a typical example of 3-spin NOE, in which you irradiate and you see on 2 sets which are closed in space, dipolar. So that's how you decide between these 2 structures, that which one is the structure. This would remain the same, this would remain the same, but this would be missing in this case, because it is no more here. NOE is actually extensively used, and I told you yesterday that NOE, the use of NOE in biomolecular NMR spectroscopy has actually earned Professor Kurt Wottrich a Nobel Prize. In this case, you have a 4.5% NOE. In this case, when you irradiate methyl, you would see 1.2. But in this case, this is an exo. This is, in this case, you would see an absence of methyl and this. No NOE would come because they are not close in space. Okay? So that's how you determine the structure of molecule. Connectivity in this indo and connectivity in this exo is exactly identical. In connectivity, all carbons are connected in an exactly similar manner. The difference is, in this case, this methyl and H is down, and in this case, this methyl and H is up. This is an indo structure and this is an exo structure. In this case, you would be, since they are up and close to this particular proton, you would be able to see the NOEs between all of them. But in this case, you would see no NOE on this proton. So you decide about indo, exo, cis, trans, positional isomer, geometrical isomer by using I told you that the NOE enhanced rate of build of NOE is proportional to the distance depending on the size, rigidity of the molecule. Kindly remember that in order to trigger a W2 longitudinal relaxation, you need to have any relaxation. Koi bhi relaxation would never happen in resonance. Any energy transfer would have in resonance. Never forget in resonance. Constructive, right? And always kindly remember that in resonance is a very important phenomena. You trigger this in resonance for W2 to happen. And that is a mechanism through which I receive the population. And that's how the intensity of I increase. So, okay, another technique which I wanted to talk very briefly, it is called diffusion order spectroscopy. Just one slide, a very, very interesting, powerful technique, still in the stages of formation. I heard of DOSY about 4 years ago, so it's so new. People are now developing various variants of DOSY. Now this DOSY is, this is the DOSY, diffusion order spectroscopy of 3 compound. Okay, now think of of 3 compound. This is, I don't know what is SDS mycelium क्या होता है? सोडियम डाइकासल्फाइड वो सही है, ये मुझे भी याद आ गया. And ATP, ये भी मुझे पता है honestly. Glucose, इसका तो मुझे पता ही है. Anyway, so these are 3 different compound, and of course water also, deuterated water, in which you have mixed them together. This is the mix of different compounds. 3 different compounds. If you want to record NMR, what you will do? क्या करें? Remember, Toxi would not work on it. Toxi works only on a spin system of the same molecule, right? Here you have 3 distinct molecules, and these 3 distinct four molecules, including water, need to be separated in order to our spectrum. Okay? Nahin? A technique was developed. People thought, what is the difference between molecules when they are together? An alcohol and a ketone, a cholesterol with penicillin, of them, what is the difference between them? What is the difference? They all carbon, they all would appear between 0 to 10, they would all appear between 0 to 220. What is the real difference between them? I mean, they are all soluble. The only difference is their diffusion coefficient. In a particular solvent, they would have a different diffusion coefficient. Capacity to diffuse in a specific solvent is a very, very property of a molecule, right? Which is different among them is coefficient. So if we have on one axis, not the frequency, but diffusion coefficient, proton chemical shift, you see this is the proton NMR of SDS micelle, this is proton NMR of ATP, right? This is the proton with reference to their diffusion coefficient. This is the line of diffusion, and this is for water. Now, the problem is solved. What you need to do is just tell them that you want a one-dimensional slice of this. And when you say a one-dimensional slice, you would get a proton NMR to a compound without isolating them, without separating them. Same with the ATP, right? An amazingly powerful technique. Problem that the purification is often difficult in compound which are either very close in size or you kindly remember that you can separate molecule on the basis of polarity and size. You know this, huh? Size. You can have a different polar compound, but the size, you can have effects of different types and other so-called encapsulation absorbent, or you can have a different polarity. When they are difficult to separate, they very often have a same or close polarity, right? For instance, if you have a let's say cholesterol, and you have another compound in which there is an additional methyl, another molecule in which we have an additional hydroxy, in another molecule you have, they all are so close to each other and they are the nightmare. Here you want NMR to work for you, and it doesn't work at that stage because the difference in diffusion is able to separate them on the basis of their diffusion coefficient. The diffusion coefficient is the property of a structure. If it's close to each other, they would have close diffusion coefficient. As a result, DOSI would never work when you need it to work. Now you would see in a month time, 6 month or a year time, an amazing new DOSY experiment design soon. I just guarantee that, in which people would be able to see a separate proton NMR spectrum of very close diffusion coefficient. They would find something different, They would do something along with the DOSY. They would have a diffusion order spectroscopy. They would do something else which makes them different also. So kindly remember that is a very powerful technique, that you have a mixture. The diffusion coefficient, you record a separate proton NMR. Your life is so easy, You do DOSY work theoretically. The only thing which you need to do is to take your plant extract and go and record DOSY, and then 5,000, right? 2 or 3 or 4. But the problem is that if they are close to structure, their diffusion close to polarity, if the polarity is so close, their diffusion and structure too, their diffusion is so close, diffusion coefficient is so close to each other to record. For instance, if the diffusion coefficient between glucose and galactose that would come here, and you would never be able to separate this, and you would see, of course, peaks, and if you just blow them, you may be able to see some peaks different from each other, but they are so close by. The difference would not be that much. So it's good news, and spectroscopy is an amazingly powerful technique which is still developing. You don't need to. Actually, what you do actually, इसका जो Pearl sequence है वो different होता है, it's altogether different. This particular compound T1 is not the frequency, it's not the time, it is the difference in diffusion coefficient which they increase with the temperature, and then vary it actually, and then they record proton NMR. I don't want to go into the Pearl sequence of this. DOSY is fairly straightforward in terms of understanding, but if you go for, and remember I told you that 2D NMR spectroscopy are frequency, but this is also a 2D NMR spectroscopy. You have and you can have an hybrid technique, hyphenated technique, LC NMR. LC means that you can have a retention time here, and you can have NMR chemical shift of each constituent with a different retention time. So the hybrid technique are also adding a dimensionality in spectroscopy. It's accepted that the dimensionality is not necessarily to be a frequency. It can be something different also. Okay. I honestly don't know, but you see, if you have a mixture, if you intentionally make, I'm sure. I recorded lots of DOSY by mixing one particular compound, a very different terpene, another saponine, or whatever, and then DOSY spectrum. I don't know whether I have it. For instance, this mixture of 2 different molecules, 3, adrenosterone, this is a plant phenolic, this is a steroid, and this is a terpene, right? This is just we mix them together. This is not the real mixture. It's not that it was obtained from a plant. Together, and you see, and proton NMR is just mixture of all 3. Recorded the DOSY, and this came as a nightmare. This is the aldehydes protons. This is the diffusion coefficient of aldehyde. This one is this one. You just make a straight line. The other side is this one. And I'm sure you would be able to appreciate that there are sets of proton. This is the sets of proton. If you make a straight line, these are proton which are on the other set. and these are the protons which are on the other side. So it was not very clear. Very simple reason came up very nicely, separate signals, but these two are not so different. So that steroids and tritopine with almost not, and you can have a nightmare. You can have very close compound like this. This is not even close. Even then doses was not so clearly working. We will still be able to identify peaks of this by just recording it, blowing it to the straight line, that which one is actually passing through, but it was not very close. Oh, just forget it. Okay, I would like to offer you anytime an email to Farhan or Mariam universities, and if you want me to appear and present myself to you for asking any question, please let them know at any time of your convenience, and I'll be happy to respond to you and have a discussion session with you. Same house, feel free to come and meet me. We are arranging for molecular medicine students, inshallah. This is, but next week, whoever wants to join me, is not obligatory, but I'm going to talk about structure activity relationship by NMR spectroscopy, SAR by NMR, drug development by NMR spectroscopy. I will talk about a swollen liquid NMR spectroscopy, and I'll talk about NMR spectroscopy next week. This is to be the part of the exam. Between today to exam, there are 16 days time. 16 days time, and during this time, kindly to you have my email, you have my telephone number, and you can also request your focal person in your universities to send me an email, and I would be happy to appear online to answer your question, respond to some of your queries. Kindly remember, the exam would not be terribly difficult. It would largely based on concepts, not on details, because I don't expect you to, and I don't expect you to remember the details. What I would ask you is largely the concepts of what modern NMR spectroscopy is. Any question? Yes?
Yes, sir. Sir, my Fardozzi, that if diffusion constant for one particular compound is changed with the change of solvent, or it is constant?
Is always different in different solvent. So you need to have a solvent. You generally have a solvent in which you have your mixture. Therefore, your component would have different diffusion coefficient, and on one axis you would have diffusion coefficient, on the other axis you would have a chemical shift. As I mentioned, compound which are very close to the polarity or the structure size, they generally have diffusion coefficient which are not so different from each other. As a result, the NMR would certainly appear, but you would not be able to recognize them so easily. The peaks would be largely overlapping with each other. Okay, do you know that chromatography, let's start chromatography from today, that chromatography is based on the separation on three different properties: polarity, size, and charge, right? For polarity, what kind of adsorbent you use? Phase. Reverse phase is also polarity. Which kind of Cefidex, size extrusion matrices, micelles, cyclodextrins, encapsulating compounds, lots of other things. For charge, ion exchange. If I give you a mixture of compound and if I tell you that I want every one of them separate, what you would do first? You would separate them on the basis of polarity. So you make pools of compound which are close to each other in polarity, right? So polarity means that you can have 6 rings with 1 hydroxy or 5 rings with 1 hydroxy. Almost. Once you have these fractions which are pooled on the basis of similar polar character, you go to which particular technique? Size. Then you separate them on the basis of size, because size extrusion chromatography is capable of separating compound on the basis of their sizes. Simple mechanical phenomena, that is smaller molecule will fit into the holes present in Cefidex, the larger molecule will elute, very small molecule will fit very nicely inside, intermediate size molecule would have a loose fitting. So you would have all of these molecules separated on the basis of size. The best strategy in the world of separating mixture is to first go for polarity based and second is size based. And if you have charge, you go for a third type of it also. Okay, thank you. Thank you very much. Assalamu alaikum. You see, FID is just induced voltage. Remember, FID is just nothing. कितने लोगों ने साइकिल चलाई है? How many people have cycles? Okay. You don't have cycle? You have cycle, right? You know that in cycle you have a light, and the light is run with a dynamo, and the dynamo is on the back of back wheel, right? The back wheel, you have a small ring which is circulating with the circle of wheel. So if you run your bicycle fast, then you see a brighter light. Is exactly the same phenomena. When you would have these wheel transfer relaxation, transverse magnetization passing in front of a detector, they induce a current, a slight current, like a dynamo. बिल्कुल जैसे dynamo में करते हैं ना इसी तरीके से. So you see the movement. If they are relaxing very fast because of very fast T1, you would have a FID which is close to each other, very, very fast. If they are moving slower because of inefficient T1, you would see a broader NOE because they would have a different frequency. And remember, rotating frame of reference. If there is no T1, there is no signal because they would never be able to have a thermal equilibrium. Remember, T2 is only losing the coherence. T2 never contribute in relaxation. It only contribute in making a signal complex, giving energy to each other. The net energy of a spin system never changed by T2. T2 is only important because it gives energy from one spin to the other, and you see the evolution, modulation, everything. Remember, but in order for the system to achieve a thermal equilibrium, T1 need to be operational. And for T1 need to be operational, it is natural because eventually you would go into solid, it will go into lattice, right? It is a problem when you have a solid NMR spectroscopy. When you have a solid sample, where the energy would go? T1 is so slow, and that's why there are lots of variants of solid state NMR spectroscopy in which you have magic angle, other things have been developed. But kindly remember that T1 is always operational in solution as state NMR spectroscopy. More or less, it can be anything, giving energy to the solvent, giving energy to the paramagnetic oxygen, impurities, other molecules, etc., etc. Okay. You see, pulses are of three different types. One is called hard pulse. When you have a whole range of chemical shift, and you're giving a pulse to everything. The block जो मैंने show किए ना in pulse diagram में the black blocks or whatever I showed were the hard pulses. The other is called soft pulses. The soft pulses are the pulses, for instance, as we have seen in saturation of S. You select one or two and then you saturate them by giving a specific frequency of radio frequency called soft pulse. There is another beautiful type of new NMR spectroscopy which is developing, is still in the phase, it's called gradient pulses. Gradient pulses mean that you have developed radio frequency oscillator which are capable of giving a pulse, but not as a hard pulse, but in a shaped pulse. Shaped pulse means that it will start with a less of radio frequency, more frequency, and then less frequency. And it is very close to what people have done in continuous wave NMR spectroscopy. This is through this Gaussian, so-called Gaussian pulses or gradient pulses, people are now trying to discover the transients of different systems, but I think it's just beyond the scope of this discussion. It's just a little too complex. किस कॉन्टेक्स्ट में लिखा हुआ है दिखा दीजिएगा मुझे बता because although we have written this book, but let me tell you that we don't remember a bit of it. It was almost 10 years ago. We're writing a new book actually. This new book would hopefully, the only thing which I need to do is to just go away for 1 week somewhere and then complete this book. This is a nice book, and it is application of NMR spectroscopy for natural product. And remember natural product, I told you earlier also that in natural product you have unknown structure, less quantities, often as a complex mixture, you have stereochemistry. And for each one of these problems, there are special hardware and softwares have been developed. So this book would have two parts. One is hardware development for natural product chemistry, for instance inverse, right? Or polarization transfer, or cryoprobes, increasing the intensity, or other hardware for magic angle spinning, and software, for example, ROSI, NOSI, APT, other things, DOSI, etc. Okay. Thank you. Anything else? Yes. Now, whoever wants to go, please go. Feel free. No problem. Yes. They need to be close in space. Close in space. NOE only comes when they are close in space. And close in space is the property you want to determine in conformation, in configuration, in different type of structural situation. That's primarily you want to know which one is close to which one. This proton, no? They're close in space. But in this case, they are far away from They're both orienting downward, right? Proton is not shown, but it is down there, right? Therefore, you would not be able to see any NOE between them. Okay. Thank you very much. Jazakallah khair. God bless you.